This is a presentation on the Handshake theorem for EECS 203, winter 2012. We are group B27, and we are Matt McAllister, Matt Muccioli, John Strichter, and Kevin Wargenka. To see this video again, and watch other videos regarding discrete mathematics and its various topics, please visit www.noatom.com. Now we will give some definitions. The degree of a vertex of a graph is the number of edges incident with it. Note that a loop at the vertex contributes twice to the degree of that vertex. The degree of a vertex of a graph is denoted deg of v, or degree of v. The degree sequence of a graph is defined as a non-increasing list of the vertex degrees of the graph itself. Now, an example of a degree of a graph problem is, what is the degree sequence of this graph? The solution is, there are 4 edges stemming from vertices 2 and 4, thus degree 4. There are 3 edges stemming from vertex 5, thus degree 3. There are 2 edges stemming from vertex 1 and 3, thus degree 2. There is 1 edge stemming from vertex 6, thus degree 1. So, the answer is 4, 4, 3, 2, 2, 1. The Handshake theorem is a statement that every finite, undirected graph has an even number of vertices with an odd degree. Another name for is the degree sum formula. It also shows that the sum of the degrees of the vertices is twice the number of edges, which is shown in the equation below. We will now do a proof of the Handshake theorem. In the notation P, Q graph, P is the number of vertices in the graph, i.e. its order, and Q is the number of edges in the graph, i.e. its size. Each edge is incident to exactly 2 vertices. The degree of each vertex is defined as the number of edges to which it is incident, so we will add up the degrees of all the vertices. We are counting all the edges of the graph twice. Now consider the sum of the degrees of its vertices. From the above, we have that k equals 2 times the number of edges, which is an even integer. Subtracting from k the degrees of all vertices of even degree, we are left with the sum of all degrees of odd vertices in V. That is the following. From this equation, you will see that this must still be an even number, as is equal to the difference of 2 even numbers. Since this is a sum of exclusively odd terms, there must be an even number of such terms for the sum on the right side to be even, hence the result. We will now show an example problem using the Handshake theorem. It has 3 parts, A, B, and C, but we will first read off parts A and B and show the solution, and then go to part C afterwards. Part A, prove that in every graph there are an even number of vertices of odd degree. Part B, conclude that at a party where some people shake hands, the number of people who shake hands an odd number of times is an even number. The solution to part A, as we showed in our proof, is that partitioning the vertices into those of even degree and those of odd degree, we know that the sum of all degrees equals the sum of all degrees that are even plus the sum of all degrees that are odd, as shown by this equation. By the handshaking theorem, the value of the left-hand side of this equation equals twice the number of edges, and so is even. The first summand on the right-hand side is even, since it is a sum of even values. So the second summand on the right-hand side must also be even. But since it is entirely a sum of odd values, it must contain an even number of terms. That is, there must be an even number of vertices with odd degree. The solution to part B is that we can represent the people at the party by the vertices of a graph. If two people shake hands, then there is an edge between the corresponding vertices. So the degree of a vertex is the number of handshakes the corresponding person performed. The result in the first part of this problem now implies that there is an even number of odd degree vertices, which translates into an even number of people who shook an odd number of hands. Part C of this problem is the following. Call a sequence of two or more different people at a party a handshake sequence if, except for the last person, each person in the sequence has shaken hands with the next person in the sequence. Suppose George was at the party and has shaken hands with an odd number of people. Explain why, starting with George, there must be a handshake sequence ending with a different person who has shaken an odd number of hands. The solution is the handshake graph between just the people at the ends of the handshake sequences that start with George is a graph. So, by part B of the problem, it must have an even number of people who shake an odd number of hands. In particular, there must be at least one other person besides George, we could call him Harry, who has also shaken an odd number of hands. So the handshake sequence from George that ends with Harry is what we are looking for. To see this video again, and watch other videos regarding discrete mathematics and its various topics, please visit www.noatom.com.